We can now use our density formula. Density is mass over volume. Substitute the mass that we calculated for the disk and the volume for the disk in to calculate the density of the disk as 2.12 times 10 to the minus 20th kilograms per cubic meter, as illustrated in equation 13. In order to calculate the mass inside the orbit of a star, I will assume the mass inside the disk is distributed uniformly. I must point out that we know that this is not true, but to simplify calculations, I choose to proceed under this equal distribution assumption. Now, to find the mass inside the orbit and inside the disk of the galaxy, we have to find the volume of the disk inside the orbit of the star. This is calculated with equation 14, where R0 is the radius of the orbit, in other words, the outer rim of the disk, and Ri is the inner radius of the disk, in other words, the radius of the bulge of the galaxy. For the first star listed in the data previously presented, the radius of the star's orbit is 1.626 times 10 to the 20th meters. That is the value of R0 in the equation 14. The radius of the bulge of the galaxy is 4.63 times 10 to the 19th meters. This is the value of Ri in equation 14. The thickness of the disk, as previously pointed out, is 9.26 times 10 to the 18th meters. Substituting all this information into equation 14 gives us a volume of the disk inside the orbit of the star, and that volume would be 7.06 times 10 to the 59th cubic meters. If we take this volume and the density of the disk and substitute it into equation 13, this allows us to calculate the mass of the disk inside the stellar orbit, and that turns out to be 1.497 times 10 to the 40th kilograms. If we add this mass to the mass of the bulge, 6.36 times 10 to the 39th kilograms, we will then have the total mass inside the orbit of this star. That turns out to be 2.133 times 10 to the 40th kilograms, and this is found in column 5 of the data presented. Similar calculations for all the other stars results in the data in column 5 for all of the stars. The sixth column of the table 1 is arrived at by substituting the values from columns 3, 4, and 5 into equation 5. That is, the radius of the orbit, the velocity of the star in the orbit, and the mass interior to the orbit. Those values substituted into equation 5 allows us to calculate the gravitational G value. If we plot column 6 versus the data in column 3, it gives us graph 3 along with its estimated trend line. If we do a sixth order polynomial regression on the data in column 6 versus column 3, we get a graph 4, with its regression equation shown and its correlation coefficient of 0.998. We have a very nice fit with the data points and the regression line. The curving up of the line at the end on the right side, I feel, is a result of reduced accuracy of the last 5 data points. If we eliminate these last 5 data points, we actually get a much higher correlation coefficient of decimal 9996, and in graph 5, a slightly different regression equation. Using the equations on graphs 4 and 5, the 2 regression equations, and if we choose various distances and calculate the G values by using the equations, we can produce a table 2. So using equations 15 and 16, we can generate this table. With equation 15, the first two columns here, these two columns, we generate, or we choose, the distance values, substitute them into the equation 15, and equation 15 then generates these g values. Similarly, equation 16, we choose the same distances, substitute them into equation 16, and that generates these g values. The masses in the Milky Way, the last column here, we get these values by following the same methods described previously, by considering these distances and substituting them into the equation 14. I will scroll down this table slowly, and you can pause it to look at the data or to copy the data or screen capture it, and so that we can talk further about it. According to table 2, the g value at a distance of 2 times 10 to the 20th meters from the center of the Milky Way is 3.578 times 10 to the negative 10 newtons meters squared per kilogram squared for equation 15, or it's 3.572 times 10 to the negative 10 newtons meters squared per kilogram squared for equation 16. If we substitute these g values into equation 4, along with the calculated mass in table 2 for that particular distance and the distance, we can calculate the velocity, or the expected velocity, of a star at a distance of 2 times 10 to the 20th meters from the center of the galaxy. And it turns out to be 2.31 times 10 to the 5th meters per second. If we look at table 1 and can look for a star that's nearly 2 times 10 to the 20th meters away from the center of the galaxy and check its velocity, we see that we are nearly dead on. To show that it's not a fluke, we can choose another distance, say 6 times 10 to the 20th meters, and substitute the g value and mass interior to that orbit, 6 times 10 to the 20th meters, calculate a velocity, 2.05 times 10 to the 5th meters per second. This compares excellently to the actual observed velocity for stars at approximately 6 times 10 to the 20th meters from the center of the galaxy. Our discussion so far has been relative to objects, stars, that are in the galaxy. If the equations are accurate or correct, they must also be true for situations where we can actually measure the value of g, like on the Earth's surface. By substituting the radius of the Earth, 6.371 times 10 to the 6th meters, into equation 15 or 16 and determine the g value that we should have at the Earth's surface, it calculates out to 6.6743 times 10 to the negative 11 newtons meters squared per kilogram squared, in agreement with measurements on the Earth. At this point, it can be stated that the velocity curve of stars orbiting the Milky Way can be explained with the simple assumption that the universal gravitational constant is not constant. That this universal gravitational constant actually varies with the radius of the star's orbit about the center of the galaxy. There is no reason to believe that the situation would be any different for stars orbiting the centers of other galaxies like the Andromeda Galaxy. If my assumption is true that the value of g varies with distance, then there is no need to explain the velocity curve of stars orbiting galaxies by introducing the idea of the elusive dark matter. At this point, I believe I have successfully accomplished the first of my two assertions that I made earlier in this video. I now move on to the second assertion, that there is no need to introduce the concept of dark energy into our physics to explain why the rate of expansion of the universe is increasing. I would like to draw your attention to the table 2 again, the last table that I just finished showing you. If we plot a graph of the calculated g values versus distance for equation 16, we obtain this graph 6. This graph 6 uses equation 16 to extrapolate beyond the range of the original data presented in table 1. Notice that at some point, at about 7.7 times 10 to the 20th meters, the curve dips below the horizontal axis. In other words, the value of g becomes negative. Recall equation 1. If g is negative, we now have a repelling force rather than an attracting force between objects. We have all of a sudden discovered our dark energy. Our dark energy is none other than gravity, which can have a repelling nature as well as an attracting nature depending upon distance. The rate at which the curve drops off is quite alarming. In fact, I believe that the curve goes negative at distances which are far too small. It would suggest that the universe is quite literally ripping itself apart, which agrees with the observations that the rate of expansion of the universe is increasing. The equation probably suggests that the rate of expansion is increasing far too quickly than what observations show. If we plot a graph of the calculated g values versus distances for equation 15 instead of 16, we obtain graph 7. In graph 7, the value of g turns negative at about 9.7 times 10 to the 20th meters, a distance that is about 1.3 times further from the galactic center. The difference between these two graphs is the erratic behavior of the last 5 data points in table 1. This illustrates how vital it is to obtain accurate data. In reality, with even better data, we may find that g goes negative at much larger distances. A comment must be made about the validity of the extrapolation. As with all extrapolations, it must be questioned as to whether it is valid to extrapolate. Extrapolations only predict possibilities. They suggest the need to design further experiments to test the prediction. By carrying out the experiments, the truth or fallacy of the prediction is determined. With experimentation, the equations we've discussed so far would end up being replaced by a more appropriate equation. Nevertheless, with these two graphs, I have shown that if my assumption that g varies with distance is true, then the need for dark energy is explained away. If g takes on a negative value, then the increasing rate of expansion of the universe is explained. In conclusion, I think it is far easier to explain what we observe about our universe by looking at the nature of the gravitational value g. Introducing the idea of dark matter and dark energy may be just complicating our picture of reality. My analysis of the data presented is by no means a proof that the value g varies with distance, but it is suggestive as a possible explanation of what we observe without introducing the difficult to find dark matter and dark energy. It would also suggest that we need to continue to refine our observations of the velocities of stars and galaxies, the masses of galaxies, the distribution of the mass within galaxies, and above all, we need to try to determine if g is a constant or not. I also wish to point out that I have introduced this idea as hypothesis. It is not even close to scientific fact, but does suggest a line of exploration for scientific endeavors. It would require further study to see if the concepts put forward here applies to other galaxies, rotation curves for those galaxies, and even to the interactions between galaxies within galactic clusters.